I will be talking about attacker behavior modeling and learning and security using deep neural networks. A common issue security agencies face is how to effectively defend their assets against adversaries. This issue is often complicated by the limited resources these agencies have in terms of money, personnel, or simply the sheer amount of assets they need to protect. We see this issue play out with wildlife protection, for example, where you have hundreds of thousands of miles of rainforest that need to be patrolled for poachers or other threats, but no number of park rangers will be able to effectively protect every square inch. So instead, you need to optimize the patrol routes these park rangers take to best deter or prevent poachers from encroaching on the land. What ends up happening is you have a type of security game playout known as the Stackelberg Security Game, where the defenders, the park rangers in this case, commit to a strategy first. Normally, this strategy is a mixed strategy, meaning it is not consistently predictable. For example, park rangers won't take the exact same route every day, because then poachers would be able to simply sidestep that specific patrol route. Instead, park rangers will strategically plan different patrol routes. That means when the poachers decide to attack in a certain area, there is a probability of that area being covered, rather than a binary it is or it is not protected. This is an example of a mixed strategy. So once the defender has decided upon their mixed strategy, the attacker, the poachers in this context, can observe and decide the best target to attack. The payoff in the Stackelberg Security Games is dependent on the defender coverage of the attacked target. This is just one example of how the Stackelberg Security Games is used. This game also plays out with Coast Guard counterterrorism efforts and airport security. This image here shows how participants play the game. Here, subjects were told the subject's reward and penalties for each target, the defender's rewards and penalty for each target, and the probability of each target being protected by a guard. What we see in this data is that people are not perfectly logical. Previous quantal response models that predictively played the Stackelberg security game operated under this assumption. However, in the subject data, we can see this assumption is flawed, as people make decisions with some subjectivity. Sometimes people make decisions based solely on the potential rewards or wary of the possible penalties. People are not always rational and predictable. This assumption of perfect rationality was updated in 2013 with the subjective utility function that was integrated into the quantal response model. This model, known as SUQR for short, would accept learned parameters from previous game data to create its output. SUQR is a linear combination of the rewards, penalties, and probabilities, which gives a better predictive output. This may be because humans are driven by simple heuristics when deciding things, but nonetheless, this method was proven effective. The shortcomings of this method, however, which we are hoping to improve upon, is that the SUQR can only take a limited set of game data. Neural networks allow for a more robust set of input features that can allow for a more comprehensive decision-making process. A neural network, as shown in this diagram here, is made up of many nodes and operates with an input layer, many hidden layers, and an output layer. This process is similar to how your own brain works. The input layer takes in information, like your eyes or ears would, and passes it to the hidden layers. The hidden layers are like your brain, with each node like a neuron, processing and moving information as needed. There can be as many hidden layers as necessary to complete the process. Finally, there is an output layer that gives you the end result, an action, if this was the human body, or the optimal target for defenders to allocate resources to in the context of the Stackelberg security games. Essentially, this project is attempting to play the Stackelberg security games in a realistic manner, incorporating the subjective and irrational components of human decision-making process, as well as the various rewards, penalties, and probabilities, and provide a layout for the optimal way to protect the defender's assets. Continuing on the wildlife protection example, the output would be the optimal patrol route for the park rangers. While this project is still in process, we have an outline of where we'll be taking it going forward. The first would be establishing the informational organization of the neural network and how many hidden layers will be needed to optimize its processing. Additionally, we are looking to modify and integrate the subjective utility function into the neural network so that the algorithm is not only accurate, but realistic and considering the more irrational sides of human decision making. We also hope to test the model's learning capabilities against the subject data set we collected to see its comparison to human response in the Stackelberg Security Games. Finally, we will be looking to grow the number of input features, since the more information the neural network has to aid its decision-making process, the better prediction we will have of how the Stackelberg Security Games will play out in a real-life context. I'd like to thank Dr. Nguyen and everyone in the AI lab, as well as the Presidential Undergraduate Research Scholars Program for supporting this project.